Right. So today we'll begin with a new topic. It is a very important topic for CSR and GATE point of view, chemical bonding, where we have to also discuss valence shell electron pair repulsion theory. We call it as, abbreviate it as VSEPR, or the other name for VSEPR is VSEPD. So that theory also we will begin today. But first let us go with a few basics of chemical bonding. Take the main heading as chemical bonding. You can expect at least 2 to 8 marks from this unit. Very small unit where molecular orbital theory is also involved. Different questions are asked. What is the structure or what is the hybridization of ClF3, or they may ask PF5 or any other example they can give. So in the last class I told you, please go through the basics and come, so that if I give you any structure, you must have an idea what is the valency of the other atom, how many bonds does it form. If you have those basics, that will be good for this topic. Okay? Right. Before entering, can anyone just explain, or can anyone tell me what is a bond? How do you define a bond? What are the types of bonds that we have? A bond is a force of attraction between the atoms, combining atoms. That could be electrostatic force of attraction, or the attraction could be due to overlapping, whatever. But there must be opposite attractions. So for example, if I consider I am taking one atom, I am taking a second atom. Both of these atoms have nuclei. They have different shells. If I consider these two atoms, there are certain electrons also. Just consider there are a few electrons. There are a few electrons also. When does these two atoms combine to form a molecule? When do these atoms combine to form a molecule? Then how will you answer it? Can any two atoms combine to give molecule? Two helium atoms I'll give. Does it combine to give you molecule? Absolutely not. They don't combine to give you molecule. You never see helium molecule or neon molecule. They exist only as atoms, atomic state only. So what is that guiding principle which is making the atoms to combine to form into a molecule? What is that guiding principle? Simple. One word answer at least. Stability. It is stability. Why do atoms combine to form molecules? Answer is stability. Why don't inert gases combine to form molecules? Inert gas atoms combine to form molecules? Again, stability. Because they are so stable, if at all they are involved in the molecular formation, they will lose stability. They can't. So for that reason, they are stable in the elemental state only. But for say hydrogen, there is another hydrogen. If you just put two hydrogens together, they are ready to combine to form a hydrogen molecule. So what is the driving force? Driving force is stability. And whenever I say stability, two factors influence stability. One, it is repulsive forces. Second, it is attractive forces. Repulsive forces and attractive forces are always there. So which of these is dominating will decide whether the molecule should form or not. Two atoms are ready to form a bond, but repulsive forces are dominating. They don't form a molecule. Two atoms are ready to form a bond. Attractive forces are dominating. Then they will form a bond. They will form a molecule. So what are these repulsive forces and attractive forces? Let us check. Within an atom, two electrons, they have like charge. So they repel. If I consider this atom, it will also have electrons. They are also like charged. They repel. So we have at least one repulsive force. There is a nucleus which is positively charged and it will attract its own electrons. It is an attractive force. Even in this atom, there is a nucleus which is attracting its own electrons. It is also attractive force. So there are repulsive forces and also there are attractive forces. But whenever these two atoms are coming closer, Then nucleus that can repel. These electrons can repel. Two repulsive forces have come. But this nucleus can also attract these electrons. This nucleus can also attract these electrons. It means attractive forces are there, repulsive forces are also coming. Whenever attractive forces dominate, that will form a molecule. So in your physical chemistry you will be seeing some Morse curves. In Morse curves spectroscopy you will be knowing it. Vibrational spectroscopy, IR spectroscopy, you will be having Morse curve. In that Morse curve, suppose if I am taking a molecule, just imagine this is one atom, this is one atom. Every atom or every molecule will not stay as such, they vibrate. Imagine I have taken HCl or I have taken a CO2, any other molecule. It is always under vibration. Now, whenever it is vibrating, can two atoms come close together and overlap? Is it so close? They come to one distance where if it is trying to come still closer, then repulsive forces dominate, because they are coming so close that nuclear repulsions will dominate. So it will not go beyond that. It will not go beyond that. If you are trying to get them very close, energy will increase. Or you are trying to get them very far away, energy will increase. But at one particular distance, energy is minimum. So that is why Morse curve, you can see U type of curve will come. If you are trying to bring atoms very close, energy will increase. If you are taking them far away, energy will increase. But at a particular distance, energy will be the least. That is what you see in the Morse curve. If you are applying more energy, bond will break. So how do Morse curve look? Potential energy curves you call it as. Potential energy curves. It is starting from here. Suppose if there is a molecule, I am trying to compress it. If I compress it, energy will be increased. If I expand it a lot, energy will increase. If the expansion is very, very high, finally the bond will break and this will just go on. They will just draw a line. It means it is no more a molecule. Atoms have totally broken. Okay? So what is the final conclusion? Final conclusion is atoms combine to give molecules so that it attains stability. And this is happening only when attractive forces dominate over repulsive forces. Okay? Whenever there are attractive forces, energy will decrease. Whenever there are repulsive forces, energy will increase. This is another point to remember. Repulsive forces increases energy. Attractive forces decreases energy. Okay? That will come in your molecular orbital theory also. If I take oxygen molecular orbital diagram, O2, or if I take carbonyl molecular orbital theory diagram, then the energy levels will not be same for heteroatom. It will be, one will be low, one will be high. The reason, whichever is more electronegative, attractive forces dominate, that will have lesser energy. So if I put carbon and oxygen, carbon monoxide molecular orbital energy level diagram, oxygen will be low, carbon will be high. 1s, 1s, 2s, 2s. Though both are 2s, though both are 1s, energies are different. Reason? Repulsive forces dominate, attractive forces dominate. Or potential energy is less for more electronegative atom, potential energy is more for more electropositive atom. Okay? So just add a note. A bond is formed between atoms. A bond is formed between atoms when attractive forces dominate over repulsive forces. Attractive forces dominate over repulsive forces. Next point. Attractive forces decrease energy. Attractive forces decrease energy, comma, repulsive forces increase energy. Attractive forces decrease energy, comma, repulsive forces increase energy. Okay, that is the conclusion for the formation of a bond. Now let me give you a general example. Right? Suppose there is a person, he or she has their partner or a lover. Just imagine. Now when they are speaking with their lover or the loved ones, how do they speak? Will they speak in a very high pitch voice or a very low voice? You might be seeing your friends, if at all they are speaking to their love mate, how do they speak? Very slowly. Even the neighbor cannot listen because they are attractive forces. But just suppose you fought with your friend and then they made a call. Then how will you speak? With a very loud voice you will speak. Just imagining that they cannot listen it. They can listen it easily. But you will be talking in a very high voice. What is the reason? Because already there have been some repulsive forces. So that repulsive forces will increase energy, but attractive forces decrease energy. The same thing atoms also follow. Attractive forces will decrease energy, repulsive forces will increase energy, and that is leading to the formation of a bond. So stability is the key. Remember, always they want to become stable. So having said this, different types of bonds are formed. Can you just tell me how many types of bonds are there? We are not going to discuss each and every basic, what is this bond, what is that bond, but just we should know what are the types of bonds. First one, we always begin with ionic bond. You can parallelly note down. The other name for ionic bond is electrovalent bond. Ionic bond or electrovalent bond. Second, covalent bond. Third one, the combination of both coordinate covalent bond. Any other bond? One more type is metallic bond. These are the four important types of bonds: ionic bond, covalent bond, coordinate covalent bond, and metallic bond. Apart from this, we have other bonds like hydrogen bond. It is like an option. And also agostic bond. Hydrogen bond and agostic bond. So how do you define ionic bond? These are electrostatic forces of attraction between oppositely charged ions. That is what we define as electrovalent bond. So there should be two oppositely charged ions. Suppose if I take sodium, sodium should be existing as Na+, chlorine should be existing as Cl-. Both are oppositely charged ions. The electrostatic forces of attraction between the oppositely charged ions is defined as ionic bond. Okay, or let me put it in a simpler way so that everyone can understand. It is just like in the ionic bond, two atoms are there. I give, you take. We will form a bond. That is ionic bond. Very simple. I give, you take. So one person is totally giving, one person is totally taking. Then they are forming a bond. That is ionic bond. On the same basis, I give, you take. On the same basis, now let us go for covalent bond. I give, you give, both will share, we will form a bond. First one was I give, you take. It is just like you bought a lunch box and your friend is eating totally, not giving it to you. Second one, you brought lunch box, your friend also brought lunch box, both are sharing. Then you are forming a bond, that is covalent bond. Third one, coordinate covalent bond. In coordinate covalent bond, I give, you don't give, but both will share and we will form a bond. So in coordinate covalent bond, only one is contributing, the other one is not contributing, but both are sharing the pair of electrons. That is coordinate covalent bond. So three important bonds that we have: ionic bond, I give you take; covalent bond, I give you give, both will share and we will form a bond; and coordinate covalent bond, only one of the participating partners will be giving a pair of electrons which is shared by both atoms, both the combining atoms. Okay, these are the three bonds that we are aware of. Again, every time we need not take all those definitions and so on. How do you define metallic bond? When I say metallic bond, two types of metallic bonds can be seen. What are they? Suppose if I take gold, or maybe I take copper, or maybe I'll take some other metal. How do you define a metallic bond? Usually metals, they are more electropositive. As they are more electropositive, they tend to lose electrons. So once they lose electrons, those electrons are loosely bound and they are free to move. Those electrons are called as free electrons. Those electrons always move. That is the reason these metals shine. Whenever light falls on them, they shine. Why do they shine? Because they are highly electropositive. The loosely bound electron will come out and it will be delocalized. It is free to move. That is called as a free electron. It is not a bound electron. It is a free electron. So we call a sea of electrons is present. A sea completely. If this is one atom, one electron is coming out. This electron is not bound with this atom. It is free to move. Second atom electron is also coming out. That is also free to move. Once this metal or once this atom has given away an electron, that is getting a positive charge. These electrons are freely moving. These electrons are creating a negative charge. There is opposite charges. So now a bond existing between a metal which has lost electrons and the electrons which are freely moving is called as metallic bond. Metallic bond is almost like your ionic bond. But in ionic bond, it is between two ions. Here it is not between two ions. A metal which has lost electrons and the electrons that have been lost, the electrostatic force of attraction between them is called as metallic bond. It is at one level. Let us understand at a second level. When we go to metal clusters and organometallics, we have say two metals. I take two rheniums, I take two titanium, or I may take two iron. These metals may have unpaired electrons in the d subshell or in the d orbitals. These electrons will form bonds. They can form a sigma bond, they can form pi bond, they can form delta bond also. They can even form phi bond. In the last classes we discussed sigma, pi, delta, phi. So they can even form sigma, pi, delta and phi. This also come under metal-metal bond. That is actually called as metal-metal bonds. It is not exactly metallic bond, metal-metal bonds. So metallic bond can be understood under two headings. One is simple metallic bond, where a metal loses electrons and the electrostatic force of attraction between the metal which lost the electron and the free electrons. That is one level. Second level, two metals can contribute their electrons and they can form metal-metal bonds. That is also discussed as a metallic bond. Okay. So all the four different types of bonds, clear? Now what is hydrogen bond? I'll give one point for each. If you want, you can note it. Just one point, not more than that. Hydrogen bond. How do you define a hydrogen bond? It is weak electrostatic force of attraction between hydrogen and electronegative atom. Can I say? What is hydrogen bond? A bond existing, a weak electrostatic force of attraction between hydrogen and an electronegative atom. But there is a small thing that you have to remember. Suppose if I give you CH, okay, I am giving you OH. So this is an electronegative atom, OH. It is an electronegative atom. This is hydrogen. What is hydrogen bond? A bond formed between hydrogen and an electronegative atom. So can a bond form here? Hydrogen bond? Yes or no? No, it can't. There is one requirement for hydrogen bond. Hydrogen bond is not just between a hydrogen and an electronegative atom. but hydrogen attached to another electronegative atom. It is a bond formed between electronegative atom and hydrogen attached to another electronegative atom. So you cannot expect a hydrogen bond for simple methane, and if I put some alcohol between methane hydrogen and alcoholic oxygen, hydrogen bond does not exist. Instead, suppose if I take OH of water molecule, I am taking OH of water molecule. Now there can be a hydrogen bond, because this is a hydrogen attached to another electronegative atom. Carbon is not highly electronegative, 2.5, just above moderate. If I consider this scale up to 4, 2.5 is just above moderate. 2, hydrogen is about 2, nearly half. When I compare with fluorine, it is nearly half of its electronegativity. Carbon is not highly electronegative atom. We don't consider it as highly electronegative. Okay? In organic chemistry, carbon is more electronegative than hydrogen, 2.5, 2.1. This is more electronegative. But when I consider oxygen, that is more electronegative atom. Fluorine, more electronegative atom. So how do I define hydrogen atom? How do I define hydrogen bond? It is a bond between an electronegative atom and hydrogen attached to another electronegative atom. That is called as hydrogen bond. Okay. Second, according to IUPAC, hydrogen bond should always be indicated by 3 dots only. 3 dots means I am just putting 1, 2, 3. 1, 2, 3. 3 dots or 3 dashes. I just cannot put OH, OH. I just cannot put these many number of dots. It is wrong according to IUPAC. So just to put only 3 dots, that will indicate that it is a hydrogen bond. Understood? Hydrogen bond? It is just a brush up. All bonds are known, but just a brush up. Maybe for the first time, some of you are hearing about agostic bond. What is this agostic bond? All other bonds you have heard right from your school times. Ionic bond, covalent bond, coordinate covalent bond, and metallic bond also. But what is this agostic bond? This is a special bond which comes in organometallic chemistry. So there we will discuss it. But simply I am telling, it is a 3-centered 2-electron bond. 3-centered 2-electron bond. 3-centered 2-electron bond means in the organometallic chemistry, metal is attached to some carbon fragment. That carbon is attached to some other ligand, and just imagine that it has a hydrogen. It has got some hydrogen. The bond formed between this hydrogen and a metal, it is coming from a carbon. Okay, it is coming from a carbon. For your convenience, directly I am taking a hydrogen here. So this is attached to carbon. That carbon is having a hydrogen. This hydrogen will form a bond with this metal. And which metal will form? A coordinatively unsaturated metal, not coordinatively saturated. It is just like just now you had a full plate of biryani and you have come. Again I am offering you another biryani. Will you eat? You will say, no, I am full. My tummy is full. But this is coordinatively unsaturated. It did not eat for one day. Now you are giving it a biryani. Then definitely it will form a bond. So it is called as a 3-centered 2-electron bond. It is taking these 2 electrons. Generally we discuss bond it like this. But where are the 2 electrons coming from? These are the 2 electrons. This will be attracted towards this metal. So that metal, which is having 16 valence electrons, it is trying to take some electron density from this CH bond and it is getting saturated. Then it will get satisfied. Okay, I am almost reaching 18 valence electron. Now I am stabilized. Such type of bond is called as agostic bond. 3-centered 2-electron bond. Where else have you seen 3-centered 2-electron bond? Anywhere else have you seen 3-centered 2-electron bond? B2H6, classic example, boranes. Boranes are the classical examples for 3-centered 2-electron bond. One of the best examples for borane is B2H6. You call it as a banana bond, but banana bond calling it at a lower level. At higher level, we don't call it as a banana bond, we call it as 3-centered 2-electron bond. Okay, agostic bond is a 3-centered 2-electron bond, right? So just write one point about each bond. First one, ionic bond. So what is ionic bond? Not by definition, by understanding. I give, you take. We will form a bond. But don't write the definition. Just remember, I give, you take, you only remember it. Write the definition for ionic bond. It is an electrostatic force of attraction. It is an electrostatic force of attraction. Electrostatic force of attraction between oppositely charged ions. It is an electrostatic force of attraction between oppositely charged ions. Oppositely charged ions. Next point. It is non-directional. It is non-directional. There is no direction for it because there is no overlapping, there is no direction. It is simply electrostatic forces of attractions. It is non-directional. Right. Now immediately one more point should come into your mind whenever I say non-directional. Can I define a geometry for ionic bond? No, because there is no direction for it. If there is a direction, there is a geometry. If there is no direction, there is no geometry. So ionic compounds do not form any geometries. They can form only lattices. Sodium chloride lattice you say. You don't say sodium chloride geometry is so and so. No. You say the lattice of sodium chloride where the coordination number of sodium or chlorine is so and so. So there is no defined geometry for ionic bond. Okay. Add it. You have written it is non-directional. Okay, continue. Therefore, there is no defined geometry. Therefore, there is no defined geometry. Next, covalent bond. General terminology, covalent bond is I give, you give, both will share, we will form a bond. That is for your remembrance purpose. I give, you give, both will form a bond. Right. Definition. Bond formed between atoms sorry, please make a correction. Bond formed by sharing of electrons. Make a correction. Bond formed by sharing of electrons. Sharing of electrons from the atoms that equally contribute electrons. That equally contribute electrons. Next point. It is directional. It is directional. It is directional. Hence, it has a definite geometry. Hence, it has a definite geometry. It has a definite geometry. Next, third one, coordinate covalent bond. Coordinate covalent bond. It is a combination of ionic bond and covalent bond. It is a combination of ionic bond and a covalent bond. Where only one of the combining atoms contribute. Only one of the combining atoms contribute a pair of electrons. Only one of the combining atoms will contribute a pair of electrons which is shared which is shared by both the atoms, which is shared by both the atoms. Next, metallic bond. Metallic bond. It is electrostatic force of attraction. It is electrostatic force of attraction between a metal that has lost electrons, between a metal that has lost electrons and the electrons that are lost, and the electrons that are lost. So it is between the metal which has lost electrons and the electrons that are lost. That is metallic bond. Next, in metal clusters, metals can combine to form metal-metal bonds. Metals can combine to form metal-metal bonds where d orbitals participate. D orbitals, not sp, where d orbitals participate to form sigma, pi and delta bonds. I am not giving phi bond, okay? I am not confusing you. So sigma, pi and delta bonds. These are the 4 important bonds. Next one, just one sentence about hydrogen bond. Hydrogen bond. It is a weak hydrogen bond. It is a weak electrostatic force of attraction. It is a weak electrostatic force of attraction between an electronegative atom and hydrogen attached to another electronegative atom, and hydrogen attached to another electronegative atom. Last one, agostic bond. AGOSTIC, agostic bond. You can write 3-centered. It is a 3-centered 2-electron bond. It is a 3-centered 2-electron bond. It exists in organometallic compounds. Where unsaturated metal forms a bond with hydrogen. Unsaturated metal forms a bond with hydrogen, which is a part of organic ligand. Which is a part of organic ligand. So next directly we have to enter into VSEPR, but before entering into VSEPR, just one sentence about Lewis octet theory. What does Lewis octet theory say? Atoms combine to form molecules, right? And these molecules are stable. Why are they stable? Because the combining atoms will obey octet rule. Therefore, they are found to be stable. But is it applicable for all the compounds that are formed? No, it was not applicable. There are some extended octet rules. Extended octet rule means they don't obey 8 electron for main group elements itself. I'm not talking about transition group elements. For main group elements itself, instead of obeying 8 electrons, extended octet rule. Extended octet means it will be more than 8 electrons or sometimes deficient, lesser than 8 electrons. Those compounds are also found to be stable. So Lewis octet rule has failed to explain the structures or geometries. First of all, it did not explain any geometry. Lewis dot structure or Lewis octet concept, it did not explain anything about geometry or any shape of the molecule. Simply it said that whatever compounds that are being formed, they obey octet rule. But there are some compounds which do not obey. They need not be always unstable. Okay, let me give you a small example. If I give you methane, how should I write the Lewis dot structure? How do we write Lewis dot structure? There is no particular geometry. So don't just put it as tetrahedra. Simply carbon is present. Carbon will have 4 valence electrons. You put just 4 valence electrons. There are 4 hydrogens. Each hydrogen is contributing 1 electron. Now you look at the central atom. In the central atom there are 1, 2, 3, 4 electrons from the carbon, and whatever electron that is being contributed from hydrogen is also taken into octet. So this is 2 electrons, 2 electrons, 2 electrons and 2 electrons. So we say carbon is satisfying octet configuration. Therefore it is stable. Nearest inert gas. If I consider hydrogen, hydrogen has got 1 electron, 1 more electron is being taken from carbon. It is taking 2 electron, nearest inert gas helium, so it is also found to be stable. So every atom is found to be stable and therefore CH4 is also stable. Okay? There is no particular geometry. It is not like any geometry. But suppose if I take PCl5. PCl5 I am just drawing 1, 2, 3, 4 and 5. For this chlorine, if I put 2, 3, 4 and 5, I am putting chlorine. Then I count the electrons. So around phosphorus, how many electrons are there? 10. But is it not stable? It is stable. PCl5 is stable. If you bring by PCl5 and keep it here, it will stay long. For many years it will stay. It is stable only. It is not obeying octet rule, but still it is found to be stable. But chlorine is obeying that octet. Chlorine valence electrons are 7. So its valence electron 7 plus 1 coming from phosphorus 8. It is obeying octet, but phosphorus is not obeying octet. So Lewis octet concept is not successful, and it could not explain any structures of the several compounds or the molecules. So for that reason we went on for the next theory, and that is most important theory for our concept. That theory is called as valence shell electron pair repulsion theory. Okay, so before VSEPR, just add a point. Lewis concept of octet, Lewis concept of octet configuration, Lewis concept of octet configuration has successfully explained the stability of many compounds on the basis of octet configuration. on the basis of octet configuration, but there are molecules which are stable without octet configuration also, without octet configuration also. Example BCl3 and PCl5. BCl3 and PCl5. So we have discussed Lewis octet configuration, where the central atom will be obeying octet rule, octet configuration. Then such atoms or such compounds are found to be stable. But there are several compounds where the central atom does not obey octet configuration, still they are found to be stable. Their properties may differ. Means, suppose if I give you some boranes, borane does not obey octet configuration, they are stable, but they act as Lewis acids. They can act as Lewis acids. That is property. We are not speaking about stability here. That becomes a property. So Lewis concept did not explain the geometries of the molecules and could not explain why some molecules are stable though they don't obey octet configuration. For this reason we are choosing a new theory. That theory is called as VSEPR theory. VSEPR theory. You have to abbreviate or you have to pronounce it as VSEPR theory only, because in some intermediate colleges I have seen a few lecturers, they will be pronouncing it as whisper theory. It is not whisper. VSEPR only, you have to pronounce it as VSEPR. Okay, so don't pronounce it as whisper theory. It is not VSPR, VSEPR. So pronounce it as VSEPR only. The other name for VSEPR? VSEPD. VSEPD. So what is the D? It is this D we are concentrating on, and this theory is depending on this D. What is this D means? I'll say this is my domain. Domain means this is my space. You should not enter into my domain. You might have seen some movies, smugglers or some villains will be there. I'll do business in this area, you do business in your area, I will not enter your area, you should not enter my area. This is my domain, this is my space, that is your space. The same thing is the concept of VSEPR. Here there are some domains given for particular electron pairs. If anything comes into that domain, repulsions will occur, and that repulsions will decide the geometry of a particular molecule. So which electrons undergo repulsions? Valence shell electrons undergo repulsions. That is what the theory say. Valence shell electron pair repulsion theory, or valence shell electron pair domain theory. That is VSEPR theory. Okay. So in VSEPR theory, whatever compounds or whatever molecules that are being formed, we try to explain their hybridizations. This is one part. We try to explain their geometries also, which is more important. because till that time they did not explain the geometries, but now this is a theory which is explaining the geometries also. When I speak about geometries, we can speak about electronic geometry as well as molecular geometry. So it can explain you about electronic geometry, it can also explain you about molecular geometry. All these things it can explain, right? So I'll give you some basics for VSEPR theory. First of all, VSEPR theory is explaining the structures of molecules, their hybridization and their geometries, right? Let me tell you, whenever atoms combine, they give you molecules. So according to VSEPR, there are two types of atoms. What are they? First, I call it as a central atom. Next one is bound atoms or surrounding atoms. So atoms, I am classifying them into two types. One is called as a central atom, another one is called as a surrounding atom or the bound atom. If I take CH4, carbon is called as a central atom and hydrogens are bounded atoms or surrounding atoms. Or if I take PCl5, which is the central atom in PCl5? Phosphorus. That you have to identify from your basics. Suppose I'll take OSCl2, which is the central atom, oxygen, sulfur or chlorine. Sulfur, that you have to identify from your basics, you will get it. So whenever I give you OSCl2, you should be able to identify which is the central atom, which are the bound atoms. So in OSCl2, sulfur is the central atom. To the sulfur, oxygen and chlorines are bound. Suppose if I take HClO4, chlorine is the central atom to which oxygens are bound. So you should identify the central atom to which there are bounded atoms or the surrounding atoms are present. Okay, so I am classifying atoms into two types. One we call it as a central atom, another we call it as a bound or the surrounding atoms. You just note that classification. This is with respect to atoms. Let me classify electrons also into two, so that this will become easy for you. Two types of electron pairs. One pair of electron we call it as bonding pair. Another type of electron pair is called as non-bonding pair. The other name is lone pair. Electron pairs are of two types: bonding pair of electrons, non-bonding pair of electrons. Let me take an example again. If I consider H2O molecule, this pair of electron is non-bonding. It is not participating in bonding, or I can call it as a lone pair. But these two electrons, one coming from oxygen, one coming from hydrogen, this is a pair, we call it as bonding pair. Whatever molecule you choose, definitely you will have two pairs of electrons. I mean, most of the molecules, not all. CH4, no lone pair, only bonding pairs. So either you will have bonding pair or you will have bonding and non-bonding pair. Okay, bonding pair, that which are participating in bonding. Non-bonding pair is called as a lone pair, which directly does not participate in bonding, according to VSEPR, not according to other theories. According to VSEPR, there are two types of electron pairs, two types of atoms: central atom, surrounding atom. Bonding pair, non-bonding pair. Then there are two types of geometries also. What are these two types? One is electronic geometry. Another one is called as molecular geometry. In the exams, sometimes they will ask you electronic geometry, sometimes they will ask you molecular geometry. You should be careful. Molecular geometry is also called as shape of the molecule. When you define shape, you don't define lone pairs. If I ask you what is the shape of water molecule, what is your answer? You say angular or bent. V shape is not exactly correct, V shape, because whenever we draw water molecule, how do we draw? There are a few conventions. Simply students will follow it. It is just like water molecule. Whenever we draw, we don't draw water molecule like this. Why do every time we draw like this, oxygen and two hydrogens? Is it a rule? No, it is just a convention. Everyone is following. But is it like a V shape? No, it is inverted V shape. So instead of calling it as V shape, the other word terminology should be used is bent or angular. That is the standard words used, bent or angular. Okay, V shape means you draw it like this, then you call it as V shape. That is fine. So when you said V shape or bent or angular, did you consider lone pairs? No, you are not considering lone pairs. You are simply defining the shape. So shape of the geometry is molecular geometry. That is called as molecular geometry. But electronic geometry means you have to say what is electronic geometry? Tetrahedra. Electronic geometry is tetrahedra. It means you are considering lone pairs as well as bond pairs. Then you consider it as an electronic geometry. You consider only bond pairs, molecular geometry. So electronic geometry means bond pairs plus lone pairs. This is only bond pairs. Consider bond pairs only. Here you consider bond pair as well as lone pair. Now you got an idea about VSEPR theory. There are two types of atoms, there are two types of geometries, there are two types of electron pairs. Sometimes there could be a single electron also. Few examples we can discuss. There are a few molecules where there is a single electron on the central atom. It is not a pair, but there can be a single electron also. About that atoms is fine, but let me just discuss about these electron pairs. Little understanding of these electron pairs. Imagine that I am taking some central atom. This is not oxygen, just some central atom I am taking. On this central atom, here I have a bond. I am just putting it as A. I am putting another bond B. There are no lone pairs here. No lone pairs, no lone pairs. So what is the shape of that molecule? No lone pairs. What is the shape of that molecule? Linear, bent, V, bent, angular, which one? What shape is it? Bent. But if there are no lone pairs, according to this theory, what they say is, this is a pair of electron, this is also a pair of electrons. What do electrons do? They always repel one another, and these repulsive forces will dominate in such a way that they go away to the maximum possible distance. You fought with your best friend. Will you stay together with them? Or if this is the room that has been given to you, you will be here, your friend will go and sit there. Opposite ends you will be. It is just like you fought with one another. Just like if this is a pair of electron, this is a pair of electron, repulsions will be there. Due to repulsions, they will choose such a space where they can be at a maximum distance possible. So what is the maximum distance possible? 180 degree. Okay, 180 degree. Suppose if I give this, it is about 130 or 140 degree. They can't be. Whenever you have only two non-bonding pairs, due to electronic repulsions, definitely they have to take up linear shape only because of repulsions. Okay, because this is bonding pair, this is also bonding pair, both are electron pairs, both are bonding pairs, they repel to the same extent. So the distance will be in such a way that the distance will be maximum between the two bonds, that is 180 degree. So it will always give you linear shape only. There is no participation of any lone pair. Okay, but I am taking another molecule where there is a central atom. There is A, there is B. This is a non-bonding pair. This is a bonding pair. This is also a bonding pair. Now I am introducing a non-bonding pair. I have introduced a non-bonding pair. Will you still expect the same linear geometry? Answer is no. Because there is a non-bonding pair of electron, this non-bonding pair is also called as a localized pair of electron. Localized pair. Localized pair will always occupy greater space. Just imagine yourself going to Maharashtra. Okay, in Maharashtra, you go and you'll say, this is my space. Can you say? Can you just say to a Marathi friend, anyone from Maharashtra here? You are there from Maharashtra. Okay, your friend has come. They'll say that this gateway of India is mine. I am local to here. Then immediately what will you say? Hey, what are you speaking? I am local. So local will try to occupy more domain because that local feeling will come. The same feeling is also there for electrons. The local electron will say, I will occupy more space. You can't be there before me. You have to go away from me. So this is a localized pair, so it will repel bonding pair of electrons to a greater extent. Repulsive magnitude will be higher for a lone pair. So this lone pair will repel this bond pair. It will repel this bond pair. It will push the bond pairs so that the geometry will not be linear. That geometry will become bent. This we call it as lone pair bond pair repulsion. Lone pair bond pair repulsion. Okay, now there are two local leaders. Both of them always fight with one another. Will they be very close? Two localites, two different groups, will they be together? No. One wants one domain, the other wants other domain. They want to occupy maximum space. They don't want to come into each other's, but they want their own separate space. So their repulsion will be the maximum. Suppose I find a lone pair, I find another lone pair, I find bond pairs. Which will repel to a greater extent means localized pairs will repel to a greater extent. So lone pair repulsion will be the maximum magnitude. Lone pair repulsion will have a maximum magnitude because they are local, they occupy more space, more repulsions. Lone pair bond pair, its magnitude will be little bit decreased comparison with lone pair. Bond pair, that repulsion is still less. Why it is still less? Because there is a pair of electron, but that pair of electron is distributed between two atoms. It is not concentrated on a single atom or central atom. It is distributed between two atoms. It is diluted. So it will say, okay, I will occupy least space. Just give me some space. So first magnitude will be lone pair. Next magnitude will be lone pair bond pair repulsive forces, and least magnitude will be between a bond pair and bond pair. That will decide the geometries of the molecules. This is according to VSEPR theory. Okay. So what is the sequence that we have? Now this shape will not be like that. The shape will shift. Lone pair repulsion will be there. If this is a central atom, lone pair will try to move away, and then it will push bond pairs. So it will acquire this kind of a shape. it is not a perfect tetrahedra also. It cannot be a perfect tetrahedra because 2 are lone pairs, 2 are bond pairs. Based on this, we have a sequence of repulsive forces, magnitude of electron pair repulsive forces. What is the sequence? Magnitude is lone pair repulsive forces will be greater than lone pair bond pair whose repulsive forces will be greater than bond pair. Bond pair repulsions are least. Okay, take down this sequence. It is just for this I have explained all those things. This is important for you. Magnitude of electron pair repulsive forces. In VSEPR they have done a classical experiment also. You can see maybe the old videos of YouTube. The best way to explain VSEPR theory is holding filled balloons. You just fill balloons equally. Then you try to hold 2 balloons with the edges where you put a band. You just try to hold the 2 balloons. How will the 2 balloons take the shape? Have you ever experimented this? You try to hold 2 balloons with their edges. Suppose if this is one balloon that you have filled, this is another balloon you have filled. Try to hold these 2. When you hold those 2, what shape does it acquire? Will the 2 balloons be like this? No. It will come like this. Linear only they will come. You try to hold 3 balloons. They will not acquire pyramidal shape. They will acquire planar shape, trigonal planar shape. You can do this experiment after going home. Just fill some balloons, 5 balloons, and then you experiment it. Definitely you will get it. Simple experiment. Completed this one, magnitude of electron pair repulsive forces. So who is more dominating means lone pair will dominate a lot. Reason, lone pair is the localized pair. Write down a point. Lone pair is a localized pair lone pair is a localized pair that occupy a greater space. Lone pair is a localized pair that occupy a greater space and will exhibit a higher repulsive magnitude repulsive magnitude. Higher repulsive magnitude. Next one, you note hybridization and their geometry. Hybridization and their geometry. I am just giving you few hybridizations and their geometries. Which d orbital is involved, that is also important for the examination point of view. For sp, sp2, sp3 it is simply p orbitals, so we are not defining. Which p orbital this could be? Suppose if I say sp2 hybridization, which p orbitals are involved? That also we can understand from group theory. When we go to symmetry and group theory, we can understand which particular p orbital is involved in carbon hybridization formation. To that extent group theory is useful for you. Right. sp3d In sp3d, if the d orbital involved is dz square, if the d orbital involved is dz square, that will give you one geometry. And if the d orbital involved is dx square minus y square, that will provide one more geometry. Hybridization is same, sp3d, sp3d, or you may call dsp3 also. Whether inner or outer d orbital is participating, based on that it could be dsp3 also. But if d orbital is dz square, one geometry. If d orbital is dx square minus y square, another geometry. Hybridization is same, sp3d, sp3d. Then sp3d2, dz square and dx square minus y square. sp3d3, dz square, dx square minus y square and dxy. What are the geometries? For sp, the geometry will be linear, sp2 will be trigonal planar, sp3 will be tetrahedral, sp3d with dz square, this is important, it has come in exams also. In trigonal bipyramidal geometry, which d orbital is involved? It is dz square only. If dz square is involved, it is TBP. If dx square minus y square is involved, it is square pyramid geometry. Apart from this, we also have dsp2, square plane geometry. For VSEPR theory purpose, it doesn't define this geometry. There is no geometry called as square pyramid as a parent geometry. There is no parent geometry for VSEPR as square pyramid. It is a derived geometry. In VSEPR, it is a derived geometry, not a parent geometry. Derived geometry means if I take a lone pair, whenever there is a lone pair, then whatever shape that the molecule is acquiring, that can be square pyramid. But directly parent geometry will not have square pyramid. It is impossible. This could be sp3d2 or d2sp3, that depends. Simply I have given for an idea sp3d2. D orbital involved could be outer or it could be inner also. If it is inner, you have to write it as d2sp3. Up till this point it is enough for VSEPR. But beyond this you can also have sp3d4, sp3d5 also. Completed? Now you blindly remember sp linear, sp2 trigonal planar, sp3 tetrahedral, sp3d with dz square trigonal bipyramidal, or for VSEPR sp3d means trigonal bipyramidal only. What do you call square pyramidal is a derived geometry, not a parental geometry. sp3d2 octahedra, sp3d3 pentagonal bipyramidal. Okay. Are you aware of bond angles? I need not give. Are you aware of bond angles? Suppose if I ask you for linear, what are the bond angles for linear? 180. Linear is 180 degree. Trigonal planar 120. Tetrahedral 109.5 degree or 109 point, yeah, 109 degree 28 minutes. So I can call 109 degree 28 minutes, or directly if I want to give in degrees, 109.5 degree, directly you take it as 109.5. It is not exactly 0.5, it will be 0.4 something, very close to 0.5, because this is 28 minutes, not 30 minutes. If it is exactly 30 minutes, this is exactly 109.5, lesser than 30 minutes, so it is 109 point, little bit less than 0.5, take it as 109.5. Trigonal bipyramidal, it will have a maximum of 180 degree between the two linear ligands. It can have 120 degree. It can also have 90 degree. Three different bond angles are present in TBP. Tetrahedra only one. Trigonal planar only one. Linear only one. Square pyramid, it can have only two bond angles, 180 degree and 90 degree. Octahedra, it can have 180 degree, it can have 90 degree. Pentagonal bipyramidal, it can have 180 degree, 90 degree and 72 degree. I'll directly give you the parent geometries. Just you should know what are the different types of geometries. I have written the bond angles. In some of the CSR exams, they have asked how many edges are coming out from a given vertex for icosahedral geometry. If you draw icosahedral geometry, for every three-dimensional geometry you will be having corners or vertices, edges and faces. From every vertex or a corner, how many edges are arising? That was the question which was asked. So now you can understand to what level the questions can be. Okay, that will come in the metal clusters. So if I give you for VSEPR, there is axe symbolism. For your understanding purpose, they have given axe symbolism. A is a central atom, X is a bonded atom, and E lone pairs. E lone pair. So if I give you any axe symbolism, AX1 E0, AX2 E0, you can understand there are two bond pairs, no lone pair, or bond pairs and lone pairs, etc. Now let me give you the geometries. Suppose if I take AX, let me take AX2, AX, AX2, both are having linear geometry. Whatever I am drawing, these are parental geometries. Without any lone pairs, directly I am giving. Next, if I take AX3, this bond angle will be 120 degree. Anywhere it is 120 degree. This is 180 degree. When it comes to tetrahedra, this is very important for you. Tetrahedra, I'll draw it separately. Any of the three you can use as tetrahedral geometry. Okay, any of the three you can use as tetrahedral geometry. So wherever I go, if I draw it like this, these two bonds are towards you, these two bonds are away from you. Orientation is different. How I am orienting it's different, but bond angle will not change. If I draw it like this, you might be thinking that it could be 90. It is not 90. Here it is not 90. Here also if I draw it like this or like this in the wedge shape, this is a two-dimensional board. Third dimension is absent in the board. So how it looks is, here the distance is looking larger. Here the distance is looking short between the bonds. But wherever you go, it is 109.5 only. Here also it is 109.5 only. Don't get confused. Here also it is 109.5. This is also 109.5. On board, on paper it looks different. In reality it looks different. So in tetrahedra, any bond angle is one and the same. Okay, don't get confused because the distance is very short here, bond angle could be less. It is not so. This is how you can orient it. It will be like 109.5 degree only. Only one bond angle for tetrahedra. Okay, it is one reason you don't have geometrical isomers for tetrahedra. But square plane, cis and trans. Why do you get cis and trans? Because you have two bond angles, 90 and 180. But for tetrahedra, only 109.5. Therefore there is no bond angle differentiation. There is no geometrical isomer possible. Next, sp3d. For sp3d, according to VSEPR, there is only TBP, but for your convenience I will also draw square pyramid. This is the equatorial plane, which is in an XY plane. One, two, three, four, five. Don't write 1, 2 because these two are axial ligands. 1, 2, and then I'll write 3, 4, 5. According to IUPAC, it is wrong. According to IUPAC, it is wrong because there is a simple rule. What does IUPAC rule say? Whatever geometry that has been given to you, first of all identify the highest fold rotational axis. In TBP, the highest fold rotational axis is C3. C3 rotational axis passing from these ligands. With respect to that highest fold rotational axis, whichever atom is towards inside, start numbering from that atom. So if you are just passing a rotational axis, imagine a TBP before you. There is a triangular planar, one ligand is above, one ligand is below. You are passing a C3 rotational axis and then rotating by 120 degree. So when you are looking from above, which atom is inside? Above is inside, below is also inside, in between they are towards outside. So start numbering from above or below atom. Anywhere you can start with. I am starting from the above atom, number it as 1. With respect to this central axis, with respect to this main axis, consider planes of atoms. Planes. Atoms are present in planes. Suppose if you consider TBP, after the break I'll bring you the model also. First atom, if you are passing a plane, there is one atom in that plane. If you are passing another plane, there are 3 atoms. If you are passing one more plane, there is one atom. First plane, second plane is taking up 3 atoms, third plane is taking up 1 atom. So whichever is inside, you have numbered it first 1. Go to the next immediate plane. This is the other plane. Next immediate plane is this. Within the next immediate plane, number should be clockwise manner only. So if I start from 2, 3, 4, or if you start 2 here, 2, 3, 4. But don't write 2, 3, 4. It should be clockwise direction only. This plane is completed. Come to the last plane, 5. So this will always be 1 and 5 only for trigonal bipyramidal geometry. Okay. Another point, this ligand is called as axial or axial position. So 2 axial ligands. This is axial. This is also axial. These three ligands are called as equatorial ligands or equatorial position. Now look at the bond angle between two axial. Here I am writing it. Between x1 and x5, x1 and x5, what is the bond angle? 180 degree. Between x1 x2, 90, or x1 x3, 90, x1 x4, 90. Because these three are in a triangular plane, this is above, so it is making 90, 90, 90. Okay, so any bond angle between x1 and x2 or x1 x3 or x1 x4, the bond angle is 90 degree. Between x2 x3, between 2 and 3 or 3 and 4 or 4 and 2, 120 degree. Bond angle is 120 degree. Between 2 3 or 3 4 or 2 4, the bond angle is 120. So three different bond angles, and the ligands are called as axial ligands and equatorial ligands. That is called as trigonal bipyramidal geometry. If I take square pyramid geometry, I cannot give it as AX5 because AX5 is according to VSEPR. So I am giving you AB5 so that there is a difference. This is AB5. How many planes of atoms? Those who have idea about symmetry, C4 rotational axis, first plane of atom 1, second plane of atoms 4, 4 ligands, central atom is always there. So how should I number it? Numbering should begin from the inner atom, so this is inner atom, next plane clockwise manner, and this is called as apical ligand, not axial ligand. That is the difference. In TBP you call it as axial equatorial, here you call it as apical and basal. You don't call these as equatorial ligands, you call it as basal ligand, apical ligand. Both are 5 coordinate geometries. 5 ligands, 5 ligands, axial equatorial, apical basal. Bond angles between B1 and B2 or B1 B3 or B1 B4 or B1 B5, bond angle is B1 B2, B1 B3, B1 B4 or B1 B5. Sorry, yeah, B1 B5. The bond angle is 90 degree. Between B2 and B4 or between B3 and B5, bond angle is 180 degree. Between B2 B3, -90 degree. Between B2 B3 or B3 B4 or B4 B5 or B5 B2, it is again 90 degree. So only two bond angles, 180 and 90. A little extension of square pyramid is octahedra. For this I can give axe symbolism. E I am not giving because E is considered to be lone pairs. This is away from you, this is towards you. Away from you, towards you. E1, E2, 3, 4, 5 in clockwise manner, E6. So there is a plane here plenty of planes. One plane I am showing. One rotational axis if I consider. First plane, second plane has 4 atoms, third plane has 1 atom. So I started numbering from the inner atom 1, second plane 2, 3, 4, 5 in clockwise manner, third plane 1 atom. Bond angles between E1, E2, between E1, E2 or E1, E3, E1, E4, E1, E5, anything. How much is the bond angle? 90 degree. On board it looks different, please check. On board most of you get confused. E1, E2 looks close, but E1, E3 looks far on board, but distance is same. 3-dimensionally distance is same. E1 to E2, E1 to E3 distance is same. It is 90 degree only. E1 to E6 or 2 to 4 or 3 to 5, 180 degree. So only 2 bond angles. One is 90 degree, one is 180. E1, E2, same E6 with E2, 3, 4, 5, 90 degree. The last geometry. Pentagonal bipyramidal. It is just an extension of trigonal bipyramidal, but the between plane is a pentagon, not a trigonal. I can give it as AX7. A is present in the center. If this is one bond above, one bond below, there is a plane with 5 more atoms. So that plane will have x1, x2, x3, x4, x5, x6 and x7. What are the bond angles? Bond angles between 1 and 7, 180 degree. Between 1 and 7, 180 degree. Between 1 and second plane of atoms, 90 degree. Or between 7 and second plane of atoms, 90 degree. So I am just giving one example. x1, x2. It could be x2, x3, x4, x5 or x6. Or I am taking x7 with x2. So with respect to third plane and second plane, with respect to first plane and second plane, bond angles will be 90 degree. And in the pentagonal plane, whatever 2 atoms that you take, between 2 and 3, or between 3 and 4, and so on, the bond angle is 72 degree. So this will be 72 degree. This will be 90 degree. And this will be 180 degree. This is 90 degree. This is 180 degree. So these are the geometries that you should be aware of. Once you are aware with the geometry, then we can enter into VSEPR, and the derived geometries. We'll just go for a break and we'll begin with VSEPR.